Okay. Today I want to kind of summarize all of this nuclear physics stuff that you've been doing. To begin with, I want to just kind of summarize some of the stuff we've already seen, and I also want to introduce you to some other ways in which the nucleus can change. At this point, the only way that you know the nucleus and the way it can change is through radioactive decay, an alpha decay or a beta decay. Remember, the word decay has to do with the graph that accompanies it as the radiation dies off. That's where we get our half-life. Alpha and beta are included under this idea of a transmutation. So a transmutation is when the nucleus changes in some way. One of the unfortunate jobs of an alchemist, if this were the Middle Ages, as he worked for the king, was to find a way to turn lead into gold. Through regular chemistry, that's an impossibility. You can't manipulate lead in chemical ways in order for it to become gold. But if the alchemists knew their nuclear physics, they might, and had enough money and had a big enough maybe particle accelerator, they may well have been able to turn that lead into gold if they could undergo the appropriate transmutations to change the number of protons in lead from 82 down to 79, could have succeeded. It's not an easy transmutation. You might say, then why aren't we doing that, turning all the lead into gold? It would be incredibly expensive. It would be quite difficult. And the amount of money that you would get from the gold after turning the lead into gold probably wouldn't pay for the energy and the material and the equipment you'd need to do it. And if you flooded the market with gold, then the price of gold would go down and you would defeat the purpose of turning your lead into gold. But we now know that artificial transmutations are possible. You can manipulate the nucleus and you can change those atoms into different atom types. So in the year 2013, that's not surprising. So here's some examples here. Alpha or beta decay are examples of natural transmutations. And what I'm going to expect you to be able to do by the end of this little section is, number one, be able to identify the type of transmutation, and number two, be able to balance a nuclear equation. We've already balanced these equations when you wrote down the examples, right? The top numbers are the mass numbers, and due to the conservation of mass, the top number on the reactant side has to equal the sum of the top numbers on the product side, right? You can't have neutrons and protons just disappearing into nothingness. There's another law that we use to balance the bottom, which is kind of like the conservation of charge. It has to do with the electrical charge. We know the bottom number to be the atomic number, but it really is also the charge number. A charge of 92 protons in a uranium nucleus, a charge of +2 in a helium nucleus, and therefore we must have thorium there. All right? Now again, I can't write on the smartboard because Smart Ink is off because it's choking, but I can use PowerPoint tools. So let's just use the pen here. What is this an example of? What type of transmutation is this? If I have a uranium, give off a helium nucleus and become a thorium. You've seen this example. We actually wrote it as the example for this particular type of radioactive decay. So this is a little bit of a review. What is that an example of? Yeah, Atlee? Yeah, that's an alpha decay. So that is alpha. And alpha, oh, and why doesn't it work? Why isn't it working anymore? Okay, let's try this. See if I can add it to it. This is where my movie's going to fail me and it's going to frustrate me. I've got to do this right in front of it or I'm going to really screw it up. Alpha decay. It's doing nothing. I tried it a minute ago. It worked. PowerPoint ink. Pen. Alpha decay. I got to do this with the mouse? Are you kidding me? That's going to be the worst writing in the world. Okay. Alpha kind of looks like a fish. It almost kind of looks like a letter A. That was a horrendous alpha. I apologize. Alpha decay. If I have a tritium, notice, mass 3, 1 proton, and it gives off that negative electron and becomes a helium, what kind of transmutation is that? Yeah. That's a beta decay. And here we go. We're going to try writing with the mouse. Woo! Beta. Beta looks like a bee, but it's got like a tail on it. This is going to be terrible. Try again here. And the bottom one, what's it? Sorry? No, it's not a gamma. We tricked you on it. It's not a gamma. Yep. It's also a beta, but the difference is we've got a positron given off here. This is an example of where that positive electron is given off as opposed to the negative. So that is also a beta, and let's see if my pen works. Doesn't work at all. What the heck? All right, beta. And really, we do, I don't care if you do it this way, but if it's a positron, we sometimes will write beta positive, beta negative. You know, it doesn't matter. If you were not to do that on a quiz or on a test, no big deal. Yep. Because in the charge of the electron, I have a negative there, meaning it's a negative charged particle with a mass of 0, because electrons are really light, and there's no negative there. And when we don't have a negative, we assume it to be a positive number, and therefore that's a positron or a positive electron. Because in a beta decay, it gives off either an electron from the nucleus or a positron from the nucleus. In an alpha decay, it gives off a helium nucleus, or we call it an alpha particle. And we've just reviewed our 2 types of nuclear radiation here at this point. That's what that was. Okay? All right. So these are natural transmutations because they just take place spontaneously. There are many artificial transmutations. Chemists, well, actually nuclear physicists, have now figured out how to take a nucleus and manipulate it and change it into a different type of nucleus. So let's take a look at some artificial transmutations. And there's one there. And again, Ernest Rutherford, remember, he found the nucleus using the alpha particles. That's pretty significant. He also named the different types of radiation. Wasn't really genius in any way. Named it A, B, and C, essentially. Alpha, beta, and gamma. Also named the nuclear strong force. Again, not very creative, but still did it. He was also the first person to be credited with an artificial transmutation. He essentially was using radioactive material and put it beside some non-radioactive material. And the particles, as they impinged on the non-radioactive material, turned the non-radioactive material radioactive. He was actually causing some of these alpha particles to stick to some of the other nuclei, changing the nucleus. So Rutherford, pretty significant scientist in the field of chemistry and nuclear physics. Even though he couldn't figure out where to put the electrons, he would have got it eventually, but Bohr beat him to the punch. Still pretty important guy. Nowadays, if you want to change a nucleus, the best way to do it is with neutrons, as opposed to protons or something bigger like an alpha particle, like a helium nucleus. Think about that for a moment. If you were to take a chlorine atom, you're all writing, and I'm talking. I'll stop talking. So in our example here, we've got a chlorine atom. Has a charge of 17, a mass of 35. We're going to fire a neutron at it. Let's imagine that we take that chlorine atom, which has a charge of plus 17, and tried to fire a proton at it, which is positive. You could get that proton to go really fast in a particle accelerator. They use different charges, like they repel it. They'll take something that's positive and give it a push, and then they change this sequentially, gives it a whole bunch of pushes and gets going really fast. But let's think about this. If you take something that's positive and you fire it at this positive nucleus, what's it going to do? What's the proton going to do when it gets close to that positive nucleus? Let's go with Atlee's arm that was going up, but we'll go with that. What's it going to do? It's going to repel away. So it's going to slow down as it gets to it. It may ultimately even repel completely away from it. And so protons were discovered to be not the greatest thing to kind of initiate nuclear change. But if I had a neutron, all right, what's the charge on a neutron? Neutral. What's going to happen to it when it encounters the nucleus? Any ideas? Sorry? It's going to get close to it. It's going to enter the nucleus. Now, it's actually, if it goes too fast, if your neutron is going fast, it actually doesn't enter it. If you've got a fast-moving neutron, it bounces off the nucleus just like if you were to have like a pool ball, you know what I mean, like a billiard ball, a cue ball, and you flung it at it, you know, really hard, and it would bounce right off. Let's say if you could, imagine you could make a pool ball made of Velcro. And then you could take another pool ball, which was the opposite Velcro. You know what I mean, the opposite Velcro? All right, okay. And if you flung that pool ball really fast at it, the Velcro wouldn't be strong enough. It would just fly off. That's exactly what happens to a fast-moving neutron. But if you have a slow-moving neutron, it gets up close, and then the attractive force of the strong force of the nucleus can take that neutron in and can cause a change in the nucleus. So you really want slow-moving neutrons in order to do this. But if you do that, it takes place. You could make some kind of unstable entity. In this case, it spits out a proton, and we're going to get something else left in the end. Let's figure out what we're going to get. That's junk. 35, 1. What am I going to have here is the mass of this new entity. Chris? 35. It has to add up to the same. What I like to do, because some of them are going to be pretty big numbers when we do some later on ones. What I like to do with this, and this is kind of a dumb example to do it with, but I'll take my calculator and I'll go 35 plus 1 equals, and then I'll subtract away all the other particles I encounter to get what my new number is supposed to be. Minus 1, oh yeah, it's 35. Thanks, Chris. And that's exactly correct. But when we get to some more complicated ones, use your calculator. Add them all up, and then subtract away, and you'll get what the mass is supposed to be on the back side. So this guy is going to have a mass of 35. Excellent. Writing with my mouse. I love it so much. Charge of 17. Charge of 0. Again, add them up. I've got to subtract away a charge of 1. What's the charge of this thing that's left? Yep, 16. And if you've got your periodic tables nearby, which I hope you do, what element is that? Sorry, sulfur? And so we have created an isotope of sulfur that has a mass of 35, and sulfur normally has a mass of 32. That's some heavy sulfur. So scientists now can easily manipulate elements to create new elements. That's how they create these heavy guys down here. Question was asked earlier on, I think in this class, might have been another one, how do they create these new elements like 115 that they recently made? They'll do an experiment like this. Now they won't just take one of these guys and add 1, but what they'll do is they'll take a one like this, and they'll try to smack like a sulfur up against it and see if they can get to 117. They'll see if they can get it to stick. It's a crazy hit and miss type deal. But when the 115 explodes apart because it's unstable and becomes different things, they can work their way backwards, and then they can say, yeah, you had a 115 for like 1/1000th of a second. Congratulations, way to go. But that's the way that works. So this is an artificial transmutation. We use artificial transmutations a lot. Nuclear reactors, the ones that we have here in Canada, in Bruce and in other side of Toronto there, Etobicoke and all that stuff. Their reactors are filled with neutrons. There's all kinds of neutrons flying around in a nuclear reactor. In northern Ontario, there's a place called Chalk River, and that is a very old, small nuclear reactor, and its sole purpose is to produce neutrons to do reactions like this. It's not there to generate energy, but it's to produce a beam of slow-moving neutrons. And what they do at Chalk River is they will make what are called medical isotopes, medical radioisotopes. So they'll create iodine that's radioactive. And if someone is suffering from a thyroid problem, iodine collects in the thyroid gland. Some biologist told me that. I don't know biology very well. Somebody told me that. Anyway, you take the radioactive iodine, it goes to your thyroid gland. Depending on how your thyroid gland is using the iodine, they can then take a picture of the radiation coming from your thyroid gland, and they can see whether it's functioning or not. All right? Various other radioactive isotopes can be used in cancer treatment, injecting a radioisotope right into a tumor to kill it. All right? So medical isotopes are created at Chalk River in Ontario, and that supplies all of North America. There actually was only two of these, one in Ontario and one in the Netherlands, and about 5 years ago, the Chalk River one had a crack in its containment system, and they had to shut it down. And then also, there was an issue with the one in the Netherlands, and there were no radioisotopes being produced for medicine, and you can't save them, because once you make them, they start to disintegrate. So there was an issue about 5 years ago. There were none around. So both of them are up and running again. I think the United States has decided to make their own because they didn't want to have to rely on ours. Anyway, that's an artificial transmutation. Let's talk about some other specific artificial transmutations. Let's see if my example, nope, the example, sorry, backing up, sorry. So, I've already mentioned the nuclear reactors. This is the reaction that happens in our nuclear reactors. Whether it's here in Ontario or Canada or anywhere, right? Even the Japanese reactors, which they're starting to shut down because of, well, if you've been reading the news, you know why. There was the big earthquake and they had damaged the nuclear reactor and it was leaking some radioactive water. So the reaction fission is what takes place in a nuclear reactor. Fission essentially means to break apart. If you've taken biology, you might learn about how something like an amoeba, well, is it amoeba? Yeah, I think so. Reproduces by binary fission. It just, pulls apart. Makes two of them. Just the same. So fission means to break apart. Not all nuclei will undergo fission. Only certain ones will do it. Take a neutron, stick it to the nucleus. It makes it unstable, but it's so unstable that it doesn't just give off an alpha particle or a beta particle. It literally rips in half and then gives off a bunch of extra neutrons. That's where the extra neutrons come from to make the radioisotopes. Uranium. But the isotope called uranium-235, it can do that. The uranium isotope that's 238 doesn't do that. So only a small fraction of uranium can be blown apart and energy obtained from it, because we get a lot of energy when that happens. The artificial element plutonium, which actually can be made from the 238. You can actually make plutonium from the 238, do a little reaction. Plutonium can do that. That's why you can have something called a plutonium bomb. At one point they were calling that. These are also the reactions that undergo in what are called fission bombs. Let's do an example of this reaction. So, uranium-235. Mass of 235, 92 protons. Stick a neutron to it. Again, it's got to be slow moving. Fast moving, bounce right off. Even though small objects like atoms and protons and neutrons have slightly different laws that govern them, still the regular laws of physics count. You have a neutron that's going way too fast, bounces right off. Have it going slow enough, it can be brought in, captured. So, add a neutron. In this case, I'm telling you what one of the chunks of the fission product is, a barium. But it doesn't have to be barium. When a uranium atom blows apart, it can break apart into multiple different fragments. But the fragments must add up to the total that we started with. So in this case, I'm just giving you barium as an example. Notice also 3 neutrons given off. That's typical as well. Not only does it blow apart, but it spits out 3 neutrons. Let's figure out what's left here on this one. So here's where the calculator comes into play, right? Because you're going to have 235 plus 1, then subtract off a 141, then subtract off, be careful here, 3. Did you subtract off 3? Did you? Yeah? What do you got? 104? Because notice we've got the 3 neutrons. How to subtract 3? 1, oh, uh-oh, oh my goodness, horrendous, 4, 104. Do we like the 104, supporters? Let's check on that. Two, that's 3, that's 1, minus 141, minus 3. I don't like 104. I got 92. I got 92. 235 plus 1, subtract 141, subtract 3. Do I have an eraser on this? Not likely. Going for the scribble. Going for the scribble. Did I say 92? 92. 92 plus 0 minus 56 minus 0. What is it? 36? 36. What is the identity of this chunk? Yep. Krypton? I got some krypton. Superman wouldn't like this. No, that has nothing to do with it. Anyway. 235 plus 1 minus 141 minus 3 gets us 92. Okay? You just have to make sure everything adds up. If you're unsure, check, add them back up. Make sure they add up on both sides. In our nuclear reactors, these neutrons, through a certain process, are slowed down, and then they get to go back and start the reaction again. In a nuclear bomb, all 3 of these will initiate 3 more reactions, which will then grow to 9 reactions, which will then grow to, I don't know what it is, a big number of reactions. And the reaction gets out of control, and you have an explosion. In a nuclear reactor, you don't want an explosion, so you have to absorb 2 of them. So there's a neutron absorbing chemical in there as well that absorbs them so they can't be available for the next reaction. And if you get it down to perfect 1 starts the next reaction, you have a nice chain reaction, and you keep that reaction running at a good speed, and the water cools it down, turns to steam, runs turbines, and we get electricity out of it. All right? So that's how we get electricity from nuclear fission. Because these particles here are moving very fast as they blow apart, and then that heats up water. Okay, so that is fission. Next, let's talk about a reaction called fusion. I am going to have you identify these. How do you determine a fission? Well, you're going to have one big element and a neutron that breaks into 2 elements, right? That's 1 breaking into 2. That's fission. Fusion is where you have more than 1 little guy that gets squeezed into 1. Fusion is where you put nuclei together. Yep.
I don't get how it breaks to the other thing.
This one guy, little piece stuck to it, doesn't count, breaks into this and this.
This and this?
This and this.
Oh, right.
This breaks apart into this and this and this. These are just chunks, like they're fragments, but that's a nucleus and that's a nucleus. One breaks into two.
Okay.
All right? One big one breaking into two, fission. Little ones. Here we've got 4 hydrogens coming together, fusing together to form a larger one. It's called fusion. And as you can see there, nuclear fusion occurs in the sun. This is the reaction that is driven by the sun. Right here is essentially the main fuel provider of the sun, this reaction here. Now, 4 hydrogens don't actually come together at one spot. That's a tricky maneuver. Whether it's chemistry or whether it's nuclear physics, to have 4 particles collide together in one spot is a rare event. It's just like cars. When cars crash, they tend to be 2 cars colliding. You might think it's a 3-car or 4-car pileup, but they didn't actually all meet at once. It would be 2, and then one might bounce off and be another 2, and one might bounce off and be another 2. Very rare to have 3 or more particles converge at one point in space at the same time. So it's something that just doesn't happen very often. But 2 things bouncing off of each other take place all the time. This actually happens as a series of steps. A couple of hydrogens get together, they spit off another piece, another one comes into that chunk, etc., etc. But this is the sum of all of those reactions put together. Take astrophysics at Western in first year if you want to learn more. And it's a killer course, man, I tell you. I got a 72. I was crushed. Anyway. Okay. Same thing, though. 1 particle left. When I get you to balance these, I'm only going to have 1 particle that's missing, and you just have to figure out the missing particle. 4 of these guys, 2 of these guys also have to come together. Their mass is 0. What's the mass of my new particle going to be? Pass the new particle? 4, yeah? 4 times 1 is 4, and so it's 4. What's the charge of my new particle going to be? Yep. Sorry? 0. I have 4 plus 1s, and I have 2 minus 1s. Yep. 2. 2. This is fun. Are we catching how the coefficient here is becoming important? What atom is this? Yep. Helium. This is not an alpha decay. An alpha decay would have a big element, and the helium would be spit out and make it into a different element, right? This is 4 hydrogen atoms being squeezed together to form a helium atom. It's not alpha. It does have the He as a product, but it's not alpha decay. This is fusion because I have a bunch of little pieces being squeezed together, little nuclei, to produce one. Okay? All right. That's nuclear fusion. Nuclear fusion has been used in bombs. What they do is they take a container that has some hydrogen in it. It's actually deuterium. It works better. And around that, they would have then the uranium or plutonium, where they would then undergo a fission reaction, produce all kind of energy to squeeze all that hydrogen together, and then that produces a fusion reaction, and it gives off a lot more energy than the first couple of atomic bombs they were using, right? So that can be used in bombs as well. Scientists have tried to make this work in a laboratory to run a nuclear fusion reaction, but it always takes a little more energy to make the fusion happen than you get out. So if you're going to run a reactor that you've got to put more energy in, that doesn't actually get you any further ahead in terms of energy production. So we do not use nuclear fusion on Earth to produce electrical energy. It's not there yet. We're close, but it's not there. I want you to write down a little summary of these particles that we've seen. And then I'm going to do a handful of just blank nuclear reactions with you. We'll try to classify them and finish them off. Then you've got a handful of questions to do. I might let you work for about 5 minutes, and then I will kind of start in on a little discussion on Niels Bohr and stuff like that. The periodic table is where you're going to find the identity of the other guys, right? If you know the number of protons, you can easily find what it is. But if you're given something that has a 0 and 1, and I have to ask you to identify the particle, let's say you're doing a nuclear reaction and the blank I leave is a neutron, what's going to happen is you'll end up with a mass of 1 and a charge of 0, and you'll have to say, huh, that's not on the table. What has a mass of 1 and a charge of 0? Oh, that's a neutron, right? So what I'm wanting you to learn from this is, right, if you had a mass of 1 and a charge of 1, what is it? It's a proton. You know what? It's also a hydrogen atom. You could put an H in place of a proton. It would still be correct. Wouldn't be wrong. If you had a mass of 0 and a charge of -1, oh, something that's really light with a -1 charge, that's an electron. It's a good old-fashioned regular electron. If you did your calculation and you found you had a mass of 0 and a charge of +1, oh, that's odd. Something that's really light and has a charge of +1, oh, that's one of those positrons. Okay? Notice the difference between the proton and the positron. Mass of 1, charge of +1, proton. Mass of 0, super light, charge of +1, positron. Electrons don't really have 0 mass, but compared to all the rest of these, they do. That's why we put 0 in there. They're so tiny. They're 1/2000th of the mass. And the good old alpha particles, 2 and 4, and you know that that's going to be a helium. And if it's an alpha particle, it's got to come from an alpha decay, not from a fusion. We'll do some examples. We'll do some examples here, and that'll give you some homework. Pausing for table completion. I'm hearing some murmuring going on. That's usually a sign that we're done writing. I will continue. Just put examples. Don't worry about writing complete the missing values for the following nuclear reactions, state the type of transmutation. We're going to do that. So just put examples, even e.g. if you wanted to. It's a very important skill to take a note that like a professor or a teacher gives you and really condense it down so you're not constantly writing. So if I have examples and da-da-da-da, just e.g. and it becomes obviously we're doing transmutation. So you can write this one down, and I've got my blank in here. Here's my blank. And once you've got the example written down, keep going. Figure out the blank. This looks like a thorium, and then we got to figure out what's missing, and then this is the other chunk. So I'm looking for a mass number. Somebody have a mass number there? Monday morning pause. Yep, what do you got, Chris? 234. 234. Fun. How about a charge number? Yep. What is it? 89 plus -1 actually gets me 88. Right? Pause for thinking. You see what I'm saying? No. If I put an 89 right there, and I add -1 to it, what is 89 plus -1? 88. You see it? Okay. So what number do I need here? Because I need this answer to be 90. Atlee, what do you got? 91. 91 plus -1 is 90. What are we looking at here? What is this thing? You're going to make me turn? Protactinium? Is it a mean one? You're not saying it because you can. What's the symbol? PA. PA. Fun. What type of transmutation is this? I don't need to tell me artificial or natural, but I'm looking for things like fission, fusion, alpha, beta. It could be just an artificial transmutation. What do we got? Beta. That's definitely a beta. Why'd you say beta? So it's got a negative E as a product. So it started as this thing and it spit out a negative electron. Beautiful. That makes good sense. Let's do the next one. Atlee is playing the role of Hermione Granger today, which is excellent. Hands up. What do you got? 222 or ZZZ? I agree. How about a charge number? Dallas? 86. Oh my goodness. There we go. And what is the element? Emily, what do you got? Radon. So Rn, is it? Rn. And that is the saddest looking Rn I've ever seen. What type of transmutation is this? Yep. Alpha. Why would you say that? Because helium is a product, and it isn't like a bunch of little guys being squished together. It's one spitting out a helium chunk. Yeah, exactly correct. Because we could have helium as a product for a fusion, right? But this is obviously helium and something else was left. Very good. Do we have troubles with my handwriting? What's the matter with you people? It's as clear as can be right there. So we're taking a nitrogen, we are firing a helium atom at it, probably a helium nucleus, and we have a proton being spit out. And what do we got here for mass number? Somebody getting that? Yep. Sorry? 13? No. Yep. Sorry? 17? I like 17. I think I like 17. I'm just doing a quick mental calculation. 14 plus 4 is 18, minus 1 is 17. Fabulous. Yep. Charge number? 8? Oh, 8 is terrible. Funny looking 8. 7 plus 2 is 9. 1, 8. Good. And what is our atom? Oxygen. And what is this called? You got an idea? Fission? What does fission mean? Fission means we're putting together or breaking it apart. Fission means we're breaking it apart. I wouldn't agree that that's fission. I don't think we're breaking these two guys apart in any way. Yeah, Emily? Fusion? I like fusion. Fusion. Oh, look at that. 2 S's in fusion? Oh, no. Oh. Yeah. Fugion. No, it actually says Fugion. Oh my goodness. You could have also put that down as artificial transmutation, all right? Because you could think of it as taking a nitrogen and having an alpha particle stuck to it and then causing that nitrogen to change into an oxygen. That's actually that first reaction that Rutherford did. So I would accept fusion because we're taking 2 little nuclei and putting them together and getting a new one with some pieces coming off. Or artificial transmutation. We've turned the nitrogen into an oxygen using an alpha particle, maybe coming from something else, which is exactly what Rutherford did. So I would have accepted artificial transmutation there as well. Gee, we've had a beta, we've had an alpha, we've had a fusion. I wonder what this is going to be. All right, teaching is not necessarily exciting in any way. They're called examples for a reason. They're examples. So again, calculator, right? 235 plus 1 minus 97 minus 2. Don't forget that coefficient in there, 2 neutrons. What do we have when we do that calculation? Yeah, what do you got? Sorry? 137? 137. And that was Haley, right? Haley? Getting names here as I'm doing this. And what do we have for a charge number? Dallas? 52? 52? 52. So what do we have here? Sorry? Tellurium. What is that, a TE? TE. So this side over here, tellurium, TE. TE. And what is this an example of? Yep. Fission. Fission. 2 S's in fission? See, that's just mean. If you're going to put fission with fusion together in nuclear reactions, one with an S, one without, it's crazy. Fission. Fission. Well, in my brain, which is not a very literate brain, it's crazy. Okay. All right, there's some examples there. There's some practice problems. I said I was going to give you 5 minutes, but I lied. So that's homework. So you can write that down. And then I am actually just going to talk for the rest of the class. Surprising, isn't it? No, because it's more of a discussion to kind of introduce you to what Bohr was thinking when he decided to put electrons into orbit. Okay, so let's, I got to stop my recording here just for a second.